Hello, my name is Zhen. I'm an applied researcher at eBay. In this talk, I'll talk about a relevance constraint re-ranking algorithm we developed in the sponsored listing recommendations. First, a bit background on the problem. On eBay's item page, we have a placement called similar sponsored items. This placement recommends sponsored items that are similar to the main item on the page, which we call seed item. To make recommendations, we first get a collection of candidates using behavior-based algorithms such as collaborative filtering and content-based algorithms such as title matching. Then we apply a gradient boost tree model on these item candidates to obtain a purchase probability for each item. Once we have the purchase probability for the item, we apply this formula to get the final score for ranking. The score is a weighted sum of the organic revenue and ad revenue. The B in the formula is the bid rate seller set for that item. Historically, we have observed a clear trade-off between revenue and the relevance. In this case, relevance is the purchase count. When we change the weight in the formula, as the weight goes up, the ad revenue term gets more influence over the final score. We will be boosting items with a higher bid rate. In this process, we could lose relevance in our recommendation. However, the fact that ad revenue still goes up means that some items still got converted. So can we make the weight a variable so that we keep the higher revenue in those converted items while not lose the purchase count in the other cases? eBay is a marketplace with vastly different listings. If a user is looking for a summer dress, there are plenty similar ones to choose from. These dresses can be similar in style, quality, and price, in which case boosting high bid rate items is unlikely to hurt the relevance. However, if a user is looking for an original Banksy art piece, all they're interested in may be other original Banksy art pieces, which aren't that many. In this case, we may be more cautious of applying high weight and boosting high bid rate items. Instead, we should rely on the purchase probability ranking model. So how do we decide the weight for each recommendation? We assume the most relevant rank list is ranking by purchase probability. See the example here. Now assume there are two different weights, W1 and W2. Based on the scoring formula, we now have two new rank lists. In this rank list, items are no longer sorted by purchase probability. For example, the original rank first place is shifted to rank second in both cases. So in the other words, the purchase probability distribution is changed. If we see the list of original probability score as the original distribution, then we can calculate the KL divergence after applying different weights. In this case, QW1 is better than QW2 because it's closer to the original ranking. We now formulate the problem as below. Given a weight space W, find the rank list that generates the highest revenue such that the rank list satisfies the constraint that its KL divergence score cannot be higher than a given constraint theta. This is a simple linear programming problem that can be solved in linear time. What if we don't want to search for the W? We now reformulate the problem as a regression. Instead of searching for the right KL divergence between the final ranking list and the original ranking list, we try to predict the KL divergence based on some characteristics of an entire recall set and a given ad revenue weight. We started with the ordinary least square regression, which fitted the promising model with an R-squared of 0.43. At inferencing time, we set the KL constraint and calculate the ad revenue weight reversely. We then tried a GPT regression. For tree-based regression, we swapped the target variable with the independent variable ad revenue weight for easier inferencing. So how did the test go? The first experiment is set up to compare the linear regression variant and the fixed weight variant. The linear regression variant showed similar revenue lift, but less purchase drop. We also plotted the revenue and the purchase count given different ad revenue weights. we now no longer see the trade-off between them like the one we saw in the beginning. The second experiment is set up to test the GPT and the gradient variant against the linear regression variant. Both showed much better performance in terms of revenue and the purchase count. If we compare the GPT and the greedy variants with the original fixed weight implementation in production, both variants resulted in very high revenue lift. The greedy variant even resulted in a slight lift in purchase. To conclude, we show that KL divergence is an effective quality measurement for re-ranked lists, and when it's applied as a global standard for controlling for good buy experience, it actually adjusts local rank list relevance individually. We show that KL divergence can be estimated through local inventory-based features. Last but not least, it's easy to implement this re-ranking approach in most of the recommendation systems to balance relevance and revenue.